This lesson explores what it means to solve for a variable, and we'll build this understanding using the idea of balanced equations. To understand balanced equations, we have to understand what an equal sign in between the two sides of an equation really means. Here's an example of an equation, x plus 3 equals 5. What does that equal sign in the middle mean? Well, imagine that I had a balance scale. And on one side, I had a box that contains some mysterious number of marbles. I don't know how many, so I'm going to let the number of marbles in there be x, because it's a number that I don't know the value of. Also on the left side of that balance scale, I have 3 more marbles. And it perfectly balances with the 5 marbles on the other side. So some unknown value of marbles plus 3 equals 5. This one we can tell pretty simply by looking at it. That how many marbles have to be inside the box? It must be 2. So we can see that we've built a physical model that goes with the equation shown at the right. And the equal sign in this case just means that the two sides of the equation balance each other, that they're equal to each other. If we were to take 3 balls away from each side of the equation, it would still balance. Again, think about the physical balance scale. If it was balanced to start with, and I took the same amount away from each side, it would still be balanced. What this looks like in algebraic notation is subtracting 3 from both sides of the equation. So we have the equation x plus 3 equals 5. We subtract 3 from the left, and to keep it balanced, to make the two sides stay equal, we take 3 away from the right. What that leaves behind then, if you look at the physical balance scale, you have nothing but x on one side, and you have 2 marbles on the other, and it balances. So x must equal 2. And we get the same thing when we do the algebra on the right. This says that how many marbles must be in the box is 2 in order to make the equation balance. So here's a more complicated example, and this time I'm going to show you the balance scale first. I have 3 boxes. Each box contains the same number of marbles as the other boxes, so all the boxes are identical. There are 3 mystery boxes plus 2 marbles on one side, and 2 mystery boxes plus 6 marbles on the other. What would an algebraic expression look like that goes with this model? Well, on the left-hand side, we would have 3 x's plus 2. Notice that's 3 mystery boxes plus 2 individual marbles. And we can't add those together. That doesn't give us 5 of anything. These are unlike terms, so we can't add them together. And then on the right, we have 2 x's plus 6 more marbles. In order to solve this, to find out how many marbles must be inside each box, we're going to take a series of steps that keep our equation balanced, that keep the two sides being equal to each other. So the first thing that we might do is to take 2 x's away from the left and 2 x's away from the right. Again, if we take the same amount off of each side, the equation stays balanced. So now we have an equation that looks like this. After we take 2 x's away from the left and 2 x's away from the right, what remains behind on the left-hand side is just 1 x plus 2 marbles, and that balances, that equals 6 marbles. Next, we would take 2 marbles away from each side, and the equation would stay balanced, because whenever we take the same thing away from both sides, it stays balanced. What that looks like in algebra is we take 2 away from each side, and we end up with x equals 4. That tells us that one mystery box perfectly balances with 4 individual marbles. Must be that there are 4 marbles inside that box. X equals 4. It's really important that the steps we take keep our equation balanced, that they keep the two sides of it equal to each other. So here's an example. We have 2 boxes on the left and 8 marbles on the right. In this case, the equation that goes with this is 2x equals 8. Another thing we can do with balance scales is we can just take half of everything on the left and half of everything on the right. That's the same thing as dividing everything on the left by 2 and everything on the right by 2. What that looks like in algebra is 2x over 2 equals 8 over 2. After we take half of the stuff off the left side of our balance scale and half off the right side, we end up with a balance scale that looks like this. It has a single x on the left and 4 marbles on the right. This is the equation x equals 4. So when we divide both sides of the equation by the same number, our equation stays balanced. So here's another example. This equation, this balance, goes with the equation 2x plus 3 equals 5. Step 1 is I want to get the balance so that it has only x's on one side and only numbers on the other. To do this, I'm going to either add or subtract the same thing to both sides. In this case, I see that if I take 3 marbles away from both sides, I'll end up with just x's on the left and just marbles on the right. The algebra for that looks like this. Subtract 3 from both sides and you get 2x equals 2. The second step is to multiply or divide both sides so that there's only one block left. Look at the left-hand side of your balance scale. There's 2 blocks there right now. So I need to cut that in half. That's dividing by 2. If I divide this in half, I end up with x equals 1. And that's the solution to our equation. That's how many marbles must have been in each box to start with in order for our equation to balance. To keep an equation balanced, there are some things you can do. You can add the same thing to both sides. Picture a physical balance scale in your mind. If you add the same thing to both sides, it stays balanced. You can subtract the same thing from both sides. You can multiply both sides by the same thing. Again, picture a physical balance scale in your mind. If you double what's on the left and you double what's on the right, it's still going to balance. Or you can divide both sides by the same thing. It's important to remember that these are the steps that you can take in order to get that variable, that x, that box with an unknown number of marbles, all by itself. The same sequence of steps is going to work when we have an equation with 2 variables and we're trying to get one of them by itself. Most often, the case where you'll have to do this is when you have an equation and you're trying to solve for y. So for example, if I give you the equation 2y plus 6 equals 4x plus 10, and I ask you to get it into slope-intercept form. Remember, slope-intercept form is y equals mx plus b. In slope-intercept form, the y is all by itself on one side of the equation. So what I'm really trying to do is to solve this equation for y. Let's build a model for this equation and then use the steps that we can apply to keep equations balanced to get the y all by itself. So first, let's build 2y plus 6. So on the left-hand side, there's 2 y's plus 6 individual ones, equals, it balances with 4 x's plus 10. So there's a picture of our equation. Now in the next step, what we're going to do is we're going to take this equation and we're going to subtract the same thing from both sides. So I notice that there are 6 marbles on the left and 10 on the right. So I can take 6 away from the left, and to keep it balanced, I have to take 6 away from the right. So now the algebra for my equation looks like this. I have 2y on the left equals 4x plus 4. I got there by subtracting 6 from both sides. The next thing that I need to do is I need to take this equation and I need to cut everything on the left in half. I have 2 y's and I want to find out what only one y is equal to. So I'm going to cut the y's on the left on half, and I'm going to cut the x's on the right in half, and I also have to cut those 1's on the right in half. Again, to keep it balanced, I have to cut everything in half. What does the algebra for this step look like? Well, I started with 2x plus 4y equals 4. I divided the 2y on the left by 2. I divided the 4x by 2. And I divided the 4 by 2. When I do that, I end up with y a single y on the left equals 2x plus 2 on the right. Now I have taken this equation and used the steps to keep an equation balanced to solve for y. I've gotten y all by itself. I still have an equation with a variable in it, x, but I've rearranged the equation so that I can see it in y equals mx plus b form. Again, when we're solving for y, we're applying the same steps that keep an equation balanced to get the y all by itself. This lesson is how to solve for y. Two other ways to think of what it means to solve for y in an equation are to get y all by itself on one side of the equal sign. And oftentimes when we do that, what we'll end up is an equation that has y equals on one side and mx plus b on the other side. Before we get into solving for y, let's remember something we did in the past. Solving for x. So at the beginning of the year, we worked on problems that look like this. Here's an example. We had a problem that said 2x plus 5 equals 9. And we wanted to get x by itself. We wanted to find out what number we had to plug in for x to make the two sides of this equation balance. The key to remember as we were solving this was to keep things balanced. We wanted to make sure that what we did to one side of the equation, we also did to the other side of the equation. So for example, the first step we did to solve this for x was we subtracted 5 from the left because we're first working to get the 2x term by itself. And to keep this balanced, we also subtracted 5 from the right. When we did that, what we had on the left was 2x plus 0, because positive 5 and negative 5 add up to 0, equals 9 minus 5 is 4. 2x plus 0 is just 2x. So what we have now is 2x equals 4. The next thing that we did was we divided both sides of this equation by 2 because we want to get the x by itself. So we'll divide the left-hand side by 2. 2 over 2 is just 1, so this becomes 1x. And to keep it balanced, we divide the right-hand side by 2, and 4 over 2 is 2. So what we ended up with is 1x equals 2. We reminded ourselves that we don't really need to write that 1 in front of the x, and so we simply wrote this as x equals 2. We got x all by itself and set it equal to something else on the other side of the equation. Solving for y is kind of like solving for x. It has some things in common. Here's an example problem that we're going to use to illustrate what solving for x and solving for y have in common. So the example problem is this: 6x plus 3y equals 9. And in this case, I'm going to remember that my goal is to get y by itself. Y equals some stuff. So my goal is to get the y in this equation all by itself. What this has in common with solving for x is that everything that we do, we have to keep the equation balanced. So whatever we do to one side of the equation, we're going to have to do to the other side of the equation. And our goal is to get the y by itself. So the first thing I'm going to try and do is to get the 3y term by itself. I notice that right now 3y has 6x added to it. So I'm going to have to subtract 6x from the left-hand side. When I do that, 6x take away 6x, that doesn't leave me anything. That leaves me with 0 plus 3y equals, on this side I have to also subtract 6x to keep things balanced. Notice that 9 and 6x are not like terms. I can't combine these. 9 is just a plain old number. And 6x, that's like taking 6 copies of a variable, x, but I don't know what number goes in place of x. So I can't combine these two terms. So I simply have to leave this as 9 minus 6x. 0 plus 3y is just 3y. And still the right-hand side is 9 minus 6x. So I've gotten the 3y term by itself, and I did steps that kept my equation balanced. Now I want to get the y all by itself. Right now y is being multiplied by 3. So to undo that multiplying by 3, I'm going to have to divide by 3. And whatever I do to the term on the left, I have to do to every term on the right to keep this equation balanced. So on the left, 3 over 3, that's another way of writing 1, y. And on the right-hand side, let's do these terms individually. 9 divided by 3 is 3, minus, that's this minus sign. 6 divided by 3 is 2, and we still have the x here. So now we have 1y equals 3 minus 2x. 1y, I know I don't have to write that 1 that's a coefficient. That really is the same thing as just plain old y equals 3 minus 2x. I've met my goal. My goal was to have y all by itself on one side of the equation and some stuff on the other side. So I have now solved this equation for y. Now notice that I still have an x in this equation, and that's okay. Solving for y doesn't necessarily mean that you get y equals a single number. It just means that you rearrange the equation so that y is all by itself here. Here's a second example of a problem that asks us to solve an equation for y. So again, we're trying to get y all by itself here. So the first thing I'm going to try and do is to get the 3y term by itself on one side of the equation. I notice that right now 3y has 4 added to it. To undo the adding 4, I'm going to have to subtract 4 from the left-hand side. And to keep the equation balanced, I'm going to subtract 4 from the right-hand side as well. When I do that, what I have on the right-hand side is still 3y. I haven't changed that. I have positive 4 and negative 4. When I add them together, I get 0. So on the right-hand side, I have 3y plus 0. On the left-hand side, I have 2x minus 4. These two are not like terms. One is a variable term. It has an x in it. One is a constant term. It's just a plain old number. And so I can't combine these together. So I simply need to write this as the expression 2x minus 4. On the right-hand side, 3y plus 0 is just 3y, and still on the left we have 2x minus 4. Now I need to remove the coefficient of 3 in front of the x. This means, in front of the y. This means 3 times y. So to undo the multiplying by 3, I need to divide by 3. If I divide the right-hand side of the equation by 3, I need to divide everything on the left-hand side of the equation by 3 as well. When I do that, on the right-hand side, I have 3 over 3 is just 1, still, times y. And on the left-hand side, 2 over 3 is 2/3. I'm going to leave that as 2/3 times x, minus 4 over 3 is 4/3. I'm going to leave that as 4/3 as well. Now I remember that 1y is just another way of writing y, and I'm just going to leave these fractions in fraction form. 2/3 x minus 4/3. Now notice that in this case we ended up with y all by itself on the right-hand side of the equation, which is fine. I didn't specifically say I needed y to be on the left-hand side or the right-hand side of the equation. It doesn't really matter. So long as y is all by itself on one side of the equation, I have effectively solved for y. So now we have this equation, y equals 2/3 x minus 4/3. It'll help us as we move into our next section to notice that this equation follows the form y equals mx plus b, where in this case, m looks like it's 2/3 and b looks like it's -4/3. This is the reason that we learn how to solve for y, how to get y all by itself, is that when we do that, what ends up on the other side of the equal sign will naturally fall into slope-intercept form for linear equations. This lesson reviews how to graph the equation of a line if it's already in slope-intercept or y equals mx plus b form. First, let's remember what it actually means to graph a line. The equation y equals 2x plus 1 and the blue line on this graph go together. What's the connection between the equation and the line? Well, the graph, that is the blue line on the graph, shows all of the xy pairs that make the equation balance, or that make the equation true. For example, when x is 0 and y is 1, the equation balances. I can check this by plugging in 0 for x and 1 for y in the equation, and I get a true statement. 2 times 0 is 0, plus 1 is indeed 1. And so I see that the point 0, 1 is on the blue line. I can do this with some other xy pairs. When x is 1, y is 3. That also makes the equation balance. And so the point 1, 3 is on the blue line. 2 and 5 for x and y also make the equation balance, and so the point 2, 5 is on the line. You can see that we could keep going forever and ever with xy pairs that make the equation balance. All of those pairs that make the equation balance are going to fall along this straight blue line. So how do m and b in y equals mx plus b help us to graph an equation more efficiently? Well, let's take the example that we used in the last slide, y equals 2x plus 1. First, let's remember that the b in this, the y equals mx plus b, the b is the y-intercept. The y-intercept is the point where our line crosses the y-axis. It tells us one point on the line. In the equation we have here, the b is 1. It's the constant that's being added. So the point 0, 1 is on the line. So I can start by graphing that one single point. The m in the equation, in y equals mx plus b, m tells us the slope. And m is the coefficient, that means the number that's being multiplied by x. Remember that slope is defined as the rise over the run. If we were to look at our equation above, the slope is 2. We're going to write that in its fraction form so that we can see the rise and the run easily. So the slope in this case is 2 over 1. That means that we rise 2 and run 1. It's like a set of directions of how to get to a second point on the line. After I've risen 2 and run 1, starting from the y-intercept, I get to a second point on the line, and that's the point 1, 3. I can rise and run again, rise 2, run 1, and I get another point on the line, 2, 5. And again, I can connect all of these points and see that that blue line is the graph of the line y equals 2x plus 1. Here's a little memory trick to help. If you already have an equation in y equals mx plus b form, the b tells you where to begin. You can plot the y-intercept, that b, first. So begin by plotting the y-intercept. The m tells you how to move. So starting from the y-intercept, because that's where you begin, the next thing you're going to do is you're going to move. You're going to use the rise to move up and the run to move over. And where you land after you've done that, that takes you to another point on the line. Then you connect those 2 points, the y-intercept, and wherever you got to by rising and running. And when you connect them, the line that connects them will be the equation of the line that you're trying to graph.